You're listening to the Bare Metal Cyber Prepcast, created to help you succeed in your Cloud Plus certification journey. Learn more at baremetalcyber.com, where additional prepcasts, books, and training materials await. Let's get started. Load balancers are essential components of cloud networking infrastructure. They distribute incoming traffic across multiple targets to improve performance, reduce latency, and ensure reliability. However, their behavior is not automatic or universal. Load balancers rely on protocol awareness, health checks, and configuration rules to operate properly. A small misconfiguration can result in failed requests, broken session behavior, or misrouted traffic. Because load balancers sit between clients and services, any issue with their configuration can disrupt visibility into which system is truly responsible for a failure. In this episode, we explore the full range of load balancer behavior issues and how to troubleshoot them from front to back. The Cloud Plus exam evaluates candidate understanding of both Layer 4 and Layer 7 load balancing mechanisms. This includes the differences between transport level and application level logic, as well as how protocols like TCP and HTTPS are handled across listeners and backend groups. Exam scenarios may involve failed health checks, improper redirect behavior, or routing failures tied to configuration mismatches. Candidates must be able to troubleshoot load balancing by examining both front-end listener settings and back-end health metrics. Understanding where traffic stops and why is essential to maintaining cloud application performance and availability. Load balancer failures can be difficult to detect at first. A service may appear to be online, but traffic does not consistently reach the intended back-end instances. Requests may succeed for one client and fail for another. Common signs include HTTP 502 and 503 errors, unexplained timeouts, or patterns where only a portion of users experience problems. Inconsistent routing or dropped connections may occur when a subset of targets becomes unhealthy or is misconfigured. Logs generated by the load balancer, including access and error logs, help identify whether requests are reaching targets or being dropped prematurely. Health check status indicators are especially important for confirming back-end availability. Listener configuration plays a key role in how the load balancer processes incoming requests. Each listener must match the protocol and port expected by the client. For example, if the front end expects HTTPS traffic but receives plain HTTP, or if the port binding is mismatched, the request may be dropped without reaching any targets. Load balancers must have properly defined listeners for each supported protocol and application. Candidates should confirm that protocol expectations, port mappings, and SSL handling are clearly specified, and that listener settings reflect actual client behavior. Back-end group health checks are used to determine whether instances or services are available to serve traffic. If health checks fail, the load balancer marks the instance as unhealthy and removes it from the rotation. The problem may not be the instance itself, but the way the health check is configured. If the health check targets the wrong path or expects a status code not returned by the application, it will fail. Timeouts that are too short or intervals that are too frequent can also cause a healthy service to be misclassified. Reviewing both the health check configuration and backend logs is necessary to distinguish between a real failure and a misconfigured probe. TLS termination, also known as SSL offloading, is the process of decrypting encrypted traffic at the load balancer level rather than passing it through to the backend. This setup requires a valid digital certificate and often uses the server name indication extension to match requests to the correct service. If the certificate is expired, mismatched, or missing from the load balancer, clients may receive handshake failures or browser warnings. It is also essential to ensure that the backend knows how to handle unencrypted traffic if TLS is terminated at the front end. Any mismatch between TLS termination and backend expectations can cause failures in otherwise valid requests. Application-level load balancers may inject headers, modify request paths, or rewrite URLs to support session tracking or routing logic. These behaviors are powerful but can introduce errors if not carefully configured. For instance, header rewrites can interfere with authentication tokens, break API gateway logic, or disrupt redirect loops. Improper path rewrites may strip required prefixes or modify routing logic in ways that the backend does not understand. Tools like curl, browser developer consoles, and proxy logging utilities allow cloud professionals to inspect what headers are added, changed, or dropped along the request path. Session persistence, often referred to as sticky sessions, ensures that a client continues to interact with the same backend instance across multiple requests. This is important for applications that maintain session state on a specific server. When stickiness fails or is not applied consistently, clients may be redirected to a different backend on each request, leading to session loss, unexpected logouts, or form resubmissions. Sticky session settings may rely on cookies, source IPs, or load balancer inserted headers. Candidates should verify stickiness settings in both the load balancer and the backend application, especially when issues occur only with multi-step transactions. Cloud-based load balancers often span multiple availability zones. Traffic distribution across these zones can break if backend instances in one zone become unavailable, or if registration fails during scaling operations. In these cases, the load balancer may continue attempting to route requests to instances that are no longer reachable. It is important to confirm that each zone contains healthy backends and that subnet configurations support load balancer access. Traffic distribution algorithms, whether latency-based, round-robin, or weighted, must be validated to confirm that they are responding properly to changes in instance health across zones. Synthetic probes and client simulation tools are powerful assets for diagnosing load balancer behavior. Tools like curl, Apache Bench, or browser-based requests allow cloud professionals to simulate traffic from various client perspectives. These tests help reveal whether traffic is reaching the backend, whether latency is consistent across paths, and whether headers or paths are being altered unexpectedly. By simulating traffic from multiple locations or devices, candidates can test regional routing, endpoint behavior, and session handling under controlled conditions. Testing backend responses directly outside of the load balancer also confirms whether the problem lies in the target system or in the balancing layer. For more cyber-related content and books, please check out cyberauthor.me. Also, there are other prepcasts on cybersecurity and more at baremetalcyber.com. For load balancing to function properly, each backend instance must be registered with the load balancer's target group or backend pool. If instances are not registered, they will not receive traffic, regardless of their health or readiness. In some cloud platforms, autoscaling groups are responsible for dynamically adding or removing instances from the backend pool. If this automation fails, or if health checks delay registration, users may see intermittent errors as the load balancer cycles through available but insufficient targets. Administrators must verify that each backend is registered and healthy, especially after deployments or scale-out events. Load balancing algorithms such as round-robin or weighted distribution determine how requests are spread across backends. If traffic appears uneven or if one backend receives disproportionate load, it may be due to misconfigured weights or interference from session persistence. Health check failures may also reduce the number of available targets, causing the algorithm to behave in unexpected ways. To diagnose this, administrators can simulate multiple requests from different clients and observe how traffic is distributed. Manually querying each backend also confirms whether load balancing is operating evenly and respecting the configured algorithm. HTTP to HTTPS redirection is a common configuration, but if misapplied, it can result in infinite redirect loops or client warnings. For example, if a listener on port 80 is configured to redirect to HTTPS without proper handling by the application, the client may be sent back and forth repeatedly. Redirects must be explicitly defined with clear 301 or 302 behavior, and the backend must support requests that arrive with HTTPS headers or terminate TLS correctly. Candidates must understand how to test these redirects with client tools and how to resolve inconsistencies between redirect policy and application response. In some environments, cross-zone load balancing is disabled by default to reduce data transfer costs. When this happens, the load balancer will only route traffic to instances within the same zone as the client-facing endpoint. If all backends in that zone are unhealthy or unregistered, requests will fail. Enabling cross-zone balancing allows traffic to be distributed across all available targets, regardless of zone. This improves availability but may increase cross-zone traffic charges. Administrators must weigh availability needs against cost considerations and explicitly enable this feature when high availability is required. Load balancers sometimes reject requests that contain excessively large headers or cookies. This often occurs in applications that use large session tokens, authorization headers, or custom metadata. When headers exceed platform limits, requests may fail with generic error messages or go unlogged. To resolve this, developers may need to optimize how session state is stored, reduce cookie sizes, or compress header data. Reviewing documentation for the load balancer platform helps clarify acceptable limits and identifies whether configuration changes can increase header size capacity. Timeout settings affect how long the load balancer waits for a response before closing the connection. If idle timeout values are too short, long-running requests such as large uploads, API responses, or video streams may terminate prematurely. These timeouts apply at both the front-end listener and the back-end connection. Matching these values is important to avoid scenarios where one layer closes the connection before the other is finished processing. Candidates should verify timeout settings across both layers and adjust them based on workload characteristics. Name resolution must be correct for the load balancer to accept traffic reliably. DNS records must point to the correct IP address or canonical name associated with the load balancer's front end. If the DNS entry is outdated or misconfigured, clients will be unable to reach the service. Additionally, some platforms offer region-specific front-end mappings, which must be verified when clients are experiencing regionally inconsistent behavior. Testing DNS resolution from both internal and external clients confirms whether name resolution is contributing to reachability issues. Every load balancer rule change should be documented, including listener updates, back-end routing changes, protocol shifts, and certificate modifications. Load balancer behavior often changes during updates, and rollback options must be clearly identified in case a change introduces new problems. Keeping a change log with timestamps, rule history, and version control references helps trace how configuration changes affect performance and stability. Documentation supports team collaboration and provides an audit trail for debugging future issues. Load balancer configuration is complex because it spans multiple layers of the network and application stack. Best practices include validating listener behavior before deployment, monitoring health checks continuously, and confirming that back-end instances are fully ready before routing traffic to them. Load balancers should always be configured with fallback behaviors such as default responses, error handling routines, or failover routing. Cloud professionals should configure alerts for high error rates, unhealthy back-end counts, or traffic anomalies. The Cloud Plus exam expects candidates to isolate failures across protocol layers, from the client's initial request to the final back-end response. Thanks for tuning in to the Bare Metal Cyber Prepcast, your trusted source for cybersecurity news and insights. Remember to subscribe at baremetalcyber.com so you never miss an update. And visit cyberauthor.me for best-selling cybersecurity books that equip you with expert knowledge. Until next time, stay secure and stay vigilant.